Hi, welcome back to this new video on kinematic indeterminacy of beams. We have already defined the kinematic indeterminacy as the number of independent joint displacements required to define the displace profile of a structure. And what are the possible joint displacements? Those are translation and rotation. In this video, we are going to see those joint displacements which are relevant to a beam. To understand that, we are going to consider this first beam here given in figure 1. We have this beam AB with a single span whose left end contains a fixed support and the right end as a roller support. In general, the kinematic indeterminacy is irrespective of any kind of loading. However, now to understand what is happening, we are considering a general loading here. Because of the application of load here, what is going to happen is the deflected profile develops is as we see here. Now, do we require any displacement that is such as, the transverse displacement here to capture the complete displace profile? No. Why? Because we are saying we require only the joint displacements. Therefore, we need to see only what is happening at the joints. Here we have two joints such as A and B. This is a fixed support, so we can't expect any translation or rotation here. However, when we move to this right support, it's a roller support. It just doesn't permit this transverse displacement, right? So this is straight away zero. What remains? This horizontal translation and then a rotation. But in case of beams, we don't consider axial deformations because when compared to the transverse deformations of a beam, these axial deformations are negligible. Therefore, we do not take into account this horizontal degree of freedom anywhere when we consider joints of a beam. And what remains? Just this rotation degree of freedom, right? That's what all it takes to capture the complete displace profile of this particular beam. We are able to see that here as well, this rotation is necessary, right? So theta b is the only displacement required for this particular case, and hence we say the kinematic indeterminacy for this beam is 1. We have another example here where the right end doesn't contain a roller support here, right? Therefore, apart from this rotation, which is possible, there is also a transverse displacement which is occurring here, which needs to be taken into account. We are marking this as delta B here. That is this transverse displacement in this direction is represented by delta B. And hence in this case, two details are required at this joint. Again, this left end is just a fixed support, so we do not have any translation or rotation here. They are straight away zero. And hence in this case, we are going to say the kinematic indeterminacy is 2. Fine. So what we can infer here is if you take any joint, only two details are required. I mean, at every joint of a beam. What are they? Those are translations and rotations, such as delta y and then theta z. If this is your x-axis and y-axis, the rotation with respect to z-axis is given by theta z. So if we take a beam, there are only two joints. The left end has delta 1 theta 1, right end as delta 2 theta 2. So we go in this particular order. First we write the transverse displacement followed by the rotation there, and then we come to the right end where we again start with the transverse displacement followed by the rotation there. That is, we give 1 for this, 2 for this, and then 3 for this, 4 for this. Why do we need that? Because in the stiffness method of analysis, what we will do is we give a unit displacement along a particular degree of freedom, locking all other degrees of freedom. And then we see what are the forces that are required to keep this particular displacement possible, right? Those forces also should be in equilibrium. So we are going to see an example here. I'm giving a unit displacement along this degree of freedom, delta 1. So as we are marking here this upward, I am displacing this end of beam by unit displacement, right? Unit amount. Whereas you can see that here I'm maintaining a horizontal uh, profile. That means the rotation here is 0, right? Similarly, if we go to the right end, this is again horizontal, which means the rotation is 0, as well as you can see that there is no displacement here. So in order to keep this configuration, what are the forces required are given by this K11, K21, K31, and K41. All right. So the first number, the first index in this represents the degree of freedom. I told for this we give 1, for this we give 2, for this we give 3, and for the degree of freedom we give 4. And second index represents what is the displacement, or I can say what displacement we are giving to get these forces generated, right? So this is the vertical force at this joint and then the moment at this joint, followed by this vertical force at this joint, followed by this moment at this joint. Therefore, we organize them along a particular column like this K11, K21, K31, K41, and this constitutes a particular column of this stiffness matrix, right? This information suffices as of now. We will come back to this later. We have one more example to understand another aspect here, then we will solve a few more problems. Here we have two spans such as AB and BC, all right? Now, because of this application of load, the displaced profile will be something like this. This end is a fixed support, right? So we don't require, there is no degree of freedom possible here. What about these two rollers? Let's first talk about this roller at the right hand and then we'll go to this roller at this location B. Now here, just this rotation is possible. So theta C I am representing here. Now when we come to this roller support here, do we really require two different rotations here and here? I mean, if we take into account the left proximity and right proximity, should there be two different values of rotation? No, because in order to maintain the continuity of this reflected profile, these two rotations should be one and same. So we are not going to mark this and this as different. Rather, you can see that these both are marked here as theta b. So this has to be borne in our mind, right? Whenever we have an intermediate support, over there, the rotation which is just to its left and just to its right should be same to maintain the compatibility requirements. All right. Therefore, in this case, we say we just require theta b and theta c to get this complete displaced profile, and hence we say the kinematic indeterminacy is 2 for this particular beam. We can summarize this overall. Okay, so wherever there is a pin support or roller support, we need to take into account 1 degree of freedom. What is that? Rotation, right? Whereas if we have a fixed support, there is no translation rotation possible, and hence the degree of freedom over there is always 0. Finally, if you have a guided roller support, the vertical displacement is possible there, and hence 1 degree of freedom is there, right? So at a guided roller, we can't expect any rotation, right? This details will be helpful when we encounter these problems here. Now we will start doing a few problems. The first one, we have three spans, AD, BC, and CD. Now we will go joint by joint to see what are the degrees of freedom possible, and then we will sum them up to get the kinematic indeterminacy, right? Let's first take these joints A and D, which are free ends. Therefore, these two ends are permitted to translate as well as rotate. Therefore, we write delta A, theta A. Similarly, we write delta D, theta D. What about these two joints? I have just summarized a while ago that whenever we encounter these two, just 1 degree of freedom is sufficient uh, to to take into account the rotation possible. So theta B and then theta c. Now we will just sum them up 1, 2, 3, 4, 5, 6. And then in this case, the kinematic inertia is 6. In this second problem, we have what we call entanglements or moment release here. The important point about a release is whenever we introduce a release at a particular joint or say a particular location in a member, what it is going to do is it is going to make the kinematic quantity corresponding to the release what we make double value. What do I mean by that is we know that when means the moment is 0. That means it is not going to allow the moment, many moments to be transferred from one span to the another one, right? What is being 0 here? M is being 0. And what is the corresponding kinematic quantity associated with the moment? It is the rotation. Therefore, at this location, the slope or the rotations will no more be single value, right? And hence we are showing it as theta b minus and then theta b plus, right? And we see that there is a kink visible here, right? So at this location, apart from these two different values of rotation, we also require what the displacement, transverse displacement. So we are marking theta b minus, theta b plus, and then delta b. And that means this is considered a joint. And at this joint, the rotation which to its left and to its right are different. Okay, but the deflection is single value. Next, we will go to the other remaining supports or joints. At this location, we have a roller support, so only the rotation is possible, theta c. And finally, when we come to this rightmost end, it's a free end. Therefore, both transverse displacement rotations are possible. Now we will just sum them up 1, 2, 3, 4, 5, 6. So in this case, the kinematic inertia is 6. Then we have this particular problem where we have a shear release at this location B. We know that at a shear release, the shear force is not transferred from one part to the another part, right? So what is the component which correspond or the kinematic quantity corresponds to the shear force is the transverse displacement. So therefore, in this case, the transverse displacement will no more be single valued and hence we will have a different value to its left and to its right, which is represented by minus and plus here. However, here the rotation will be single value, right? These two ends are fixed ones, so we don't have any degree of freedom over there. Finally, we will sum them up 1, 2, 3. So in this case, the kinematic energy is 3. So in this fourth problem, we see something different. We have also included the moment of inertia values. We see that for the span AB, it is I1. For the span BC, it is n times I1 where n is not equal to 1. If we contrast this with the beam, with a beam in wherein the moment of inertia is constant throughout, this beam is kinematically determinate. That means K is equal to 0 for this case. But whenever the moment of inertia changes, what happens is in the stiffness method of analysis, we need to consider this as two elements, this separate and this separate. That is AB as one element and BC as one element. In that case, this is going to act like a joint, and hence at this location, we need to take into account the transverse displacement and the rotation degree of freedom. So in this case, kinematic inertia is 2. These two details are required to capture the displaced profile of the beam after the application of load. Finally, we have this fifth problem in which we have three spans A, B, B, C, and C, D. And again, I'm marking here different values of moment of inertia, right? Why do I do that? Because in the previous problem, I told whenever the moment of inertia changes, we need to introduce one additional joint. But in this case, do we require that really? The answer is no. Why? Because wherever the moment of inertia changes, already we have a support, right? Therefore, beforehand, we will discretize this as three elements, right? Which will automatically take care of this change in moment of inertia values. Now we will go just joint by joint to find out the kinematic inertia. This is a greater roller support, so only transfer is possible. Delta A, these two at these two locations only these two rotations theta B and theta C respectively are possible, and hence we can directly say the kinematic inertia is 3 here. This is a fixed support anyway, right? So apart from those support conditions, the common idea one should have about these releases in case of a beam particularly are as follows. Whenever we have an internal hinge, at that internal hinge, we need to consider 3 degrees of freedom. Similarly, whenever we have a shear release at those locations, we need to take 3 degrees of freedom into consideration. Because at an internal hinge, what happens? These rotations will be double valued. However, this displacement is single valued. The converse happens whenever we come across a shear release. That is, the displacements will be double valued and the rotation will be single valued. So to account for these three in each case, we need to consider 3 degrees of freedom. All right. So hope this helps. With this we'll wind up this video, and the next video we'll see the kinematic inertia of frames. Thanks a lot.